So we are going to be talking about something called an identity. In fact, in particular, we're going to be talking about trigonometric identities. But let's just look at a couple things. What do these all have in common?
They all go for it.
Yeah, they're all expressions that equal 4. Now, these are pretty simple, so it doesn't take too much brain power to say that they're all the same. And now if I were to take something like this, and this, and how about these are, take a look. These are also all kind of the same. I mean, they look different. So, how is it we would show that one of these is equivalent to one of these? Well, we have to use some rules of algebra. Yeah, you can call it simplifying, but we're constrained here. I mean, if you want to get really specific, we could apply the distributive property. Right? So this is 2 times x minus 2 times 3. And here we rewrite. Here again, there's kind of a distributive property here. Kind of like x. We would never do this because it's too obvious, but this would be 2x minus 6. And here, well, we break it up into 2 fractions. And again, we get 2x minus 6. So these are all equivalent, and the second example is a little different from the first example. In what way? There's an x, yeah, as a variable. But you can see in the second example, it doesn't matter what x is. X could be any number. These would always be the same. And we kind of demonstrated that. We could demonstrate it in a more formal way. We could do a proof. Right? We could say, we could present it as a theorem. Let's see, push this up here. We could say, if A is equal to 2 times x minus 3, then A is equal to x plus x minus 6. That would be a theorem. Very simple theorem, and we could prove it. We'd go step by step. Remember proofs from geometry, step by step. In a very formal proof, you might indicate each step along the way, what property you're using. Or if it's obvious to you, it's probably obvious to me, obvious to a mathematician, you don't really have to show it. You can just say, well, A is equal to 2x minus 3, and A is clearly equal to 2x minus 6, and furthermore, it's equal to x plus x minus 6. Each of these steps has a description, right? Distributive, property, well, I kind of skipped a step if we want to get real heavy. But, you know, this is all pretty straightforward. Now, in doing a proof, there's kind of a catch, right? You could say, well, let's start with this, x plus x minus 6, and work our way back. And in a formal proof, that's not a good idea generally. Does anyone know why? I know this goes back to your geometry class. You may have learned this. You can't prove something by assuming it's true, right? If I assume A is equal to this, I could, you know, find my way back, but that wouldn't necessarily be a valid proof. However, in this case, I could kind of do that, because if I just reverse these steps, each of these steps is reversible. So when we get into trigonometric identities and proving them, you want to be a little careful. There's certain steps you're going to take to kind of show how you get from here to there. But you want to be careful that, when you show the identity is true, you prove it, you start kind of from what you know and get to what you're trying to prove. I don't know if I said that very clearly, but I'll give you examples to show you what I mean. Okay, so again, as I mentioned, we're going to talk about trigonometric identities, and we're going to start by listing some things which the book calls trigonometric identities. The book calls them fundamental identities. They're not identities. Okay? I'll just start with this one. Tangent theta equals sine theta over cosine theta. Now, you can treat this as an identity. We're going to treat it as an identity, but it's a definition. It's a very subtle difference. Definitions are true merely because we say they're true. This is what the tangent is. The sine divided by the cosine. We have a few more of these. Cotangent theta is what?
Cosine over sine.
Cosine over sine. And secant theta, again, this is a definition. What's the secant? 1 over cosine. And cosecant is just 1 over sine? 1 over sine. Okay. So we're going to start accumulating some basic fundamental identities out of your bag of tricks or put on your cheat sheet. And all these, you don't have to justify them. As I said, they're definitions, but once we've shown something to be the case, you can use it. All right, the first real identities we're going to look at are things that we actually talked about earlier. Let's go back to the definition of sine and cosine on a unit circle. So the x is the cosine of theta, and the y is the sine of theta. So I want to look at for a second just what would be negative theta be? Well,
Cosine theta and negative sine theta.
the cosine theta and negative sine theta. That's certainly true in the first quadrant, because the negative is going to be down here in the fourth. And it's also true in the second quadrant, because the negative is going to be down here in the third. So our first real identity is that sine of negative theta is the negative of the sine of theta.
It's the same here for cosine and sine.
It's not true of cosine. We're going to do that next. Now, in particular, functions that follow this form, f of negative x equals negative f of x, have a name. They're called odd functions. Okay, let's look at the cosine for a second here. Here we have theta and negative theta. The cosine being the x-coordinate, what do we know? They're the same, aren't they? This is, sorry, cosine of negative theta. Sine of negative, well, it is negative sine of theta. It's the same, right? It doesn't change sign. So here we have something a little different. Here we have cosine of negative theta equals cosine of theta. And again, functions that have this form, f of negative x equals f of x, have a special name. They're called even functions. I know we talked about these in the class earlier. I have some room here. I'll make some room. There's something about the graphs of odd and even functions you should know about. If I take the cosine function, an even function, if you look at its graph, the left side will be a mirror of the right side. So, for example, if you think of y equals x squared, the parabola, right? That's going to be an even function. All right, so we start off, okay, we've got some fundamental identities here. And now we're going to try and prove a new one, right? We're going to try and prove that the tangent of negative theta is equal to negative tangent of theta. We're going to try and prove tangents. What kind of function?
It's not.
Odd function. Okay. So, first step. Tangent of negative theta. We're going to use an identity. Tangent of negative, well, actually the definition. That's the sine of negative theta over the cosine of negative theta. Right? Here I'm just plugging in the definition of tangent, being the sine over the cosine. Okay, so now let's use my identity from over there. What is the sine of negative theta?
Negative sine theta.
Negative sine theta. And what is the cosine of negative theta? Cosine theta. So here I have the negative sine over the cosine, but that's just the negative tangent by the definition. So here we see we've shown our identity, we've proven it. that's pretty straightforward. I'm not going to go through the, because it's so simple, I'm not going to go through the whole process for these other functions, but let's look at the cotangent of negative theta. What do you suppose that's equal to in terms of cotangent?
Negative cotangent theta.
Negative cotangent.
It's the exact same thing as tangent theta, just cosine and sine.
Yeah. There's another way we could show it. We could just take this identity and find its reciprocal. That would do the same thing. Very quickly, the secant of negative theta. Well, you can just guess this one. If the secant is 1 over the sine, and the sine is an odd function, this is going to be an odd function. I'm sorry, 1 over the cosine, it's an even function. So the secant of negative theta is just the secant of theta. And you should be able to guess by now the cosecant, negative theta, is what?
Negative cosecant.
Yeah, there's the odd function. Okay, these are very, very simple identities, basic identities. You need to kind of take these to heart. You need to, you know how to do fractions, you know how to multiply. You should know these identities. Any of you who move on to calculus, when you get to calculus deals with the trig functions, these are going to be kind of the nuts and bolts. They're not going to be the calculus, but they're going to be something you're going to need to know how to do kind of off the top of your head. Okay. I think I'd like to do an example I want to do here. All right. This is an identity I'd like to prove. Okay, so now I'm going to give you the most important strategy for doing these problems. Some of them are going to be hard. This one's pretty easy. All right, the first strategy is when you have something like this, convert it all to sines and cosines and see what drops out. So let's start with this side. The tangent is what?
Sine of the cosine.
Sine over cosine. The cosecant is
1 over sine.
1 over the sine.
And 1 over cosine.
And the cosine is
Cosine.
the cosine. Well, you can cancel the sine, cancel the cosine. We just get 1. Now, there's something a little nitpicky I want to point out here. Is this true for all theta?
Yeah.
Those two are functions there.
This is a tricky question. Is this true for all theta? What about theta equals 0? So the tangent of 0 is
0.
0.
Right there, you know everything else will be 0.
Yeah, we've already got a problem. The cosine of 0 is, it's over here, that's 1. And the cosecant of theta is undefined, yeah. So, if you're going to do rigorous mathematics, you'd have to be a little careful. You'd have to say where theta is defined, where this side is defined, or, where sine and cosine are not 0. We're not going to have to do, you're not going to have to do that in this class. It's just going to be assumed that whenever we show an identity, we're only concerned about places where both sides of equal sign are defined, where all the components are defined. So you don't have to worry about it. I'm mentioning it because, some of you might go, wait a minute, that's not always true. Okay. All right. This is a typical kind of problem you'll need to solve. You need to show that this identity is true. And that's more or less how you're going to do it, step by step. And again, the first strategy is look for turning everything into sines and cosines, seeing if that doesn't get the answer to drop out. Okay. The next set of identities are called co-function identities. And let's see what I mean by that. Oops, I got a table here. So, I'm going to draw a triangle here. I'll call this angle theta, and I'll call this angle alpha. What do we know about alpha and theta? Complementary. Complementary, right? Which just means that theta plus alpha equals 90 degrees. Okay, let's draw in some sides of the triangle, x, y, we'll call this r. And we know that the sine of theta is what? It's just y over r. But if in your head you can kind of turn this triangle sideways, what's the cosine of alpha? It's also y over r. So we have that the sine of theta is equal to the cosine of alpha. But alpha, if I solve for it here, you can see alpha is just 90 degrees minus theta. So let me write that out. Sine of theta equals cosine of 90 degrees minus theta. So because we're dealing with complementary angles, these are called co-function identities. The co coming from complementary. Similarly, you could show that the cosine of theta is x over r, and the sine of alpha is x over r. These being equal, we're going to get cosine of theta equal to sine of 90 degrees minus theta. All right, co-function identities. All right. Let's ask a question. Is there a co-function function identity for the tangent. Well, tangent is the sine and cosine. But applying our identities, it's the cosine of 90 minus theta over the sine 90 minus theta. Well, what's the cosine over the sine of something? Cotangent. So, you see here we have a nice identity for the tangent. What about secant? What's going to happen with secant? Well, secant is 1 over cosine, which is 1 over the sine of 90 minus theta. Well, what's 1 over the sine?
Using myself in here because
It's going to be cosecant of 90 minus theta. One of the things we're doing here is we're kind of building, kind of building blocks. What have we got here? We've got the definitions of tangent, cotangent, secant. We're treating those as identities. We have these odd-even identities. Now we have these co-function identities. These are all things that we're going to use when we're trying to show somewhat more complex identities. Okay, let's do kind of let's do a more computational kind of problem for a second. I'm gonna pull a fast move here.
not fast.
I'm going to switch from degrees to radians, not to throw anybody off. Seems like the book wants to do this. So if I say the cosine of pi over 2 minus theta is equal to 0.8, I want to solve that. I want to solve it for all theta between 0 and 2 pi. We've done problems like this, but before I apply the inverse cosine, I could do something else here. I could use an identity. What would I substitute here? Yeah, just sine theta equals 0.8, or theta equals inverse sine of 0.8. And as we've done these before, your calculator will tell us some value here, which is in the first quadrant. And then where else are we going to find the sine? Over here, where else are we going to find the sine? Kind of over here. It's complement. Okay, one more example using these cofunctions. What if I wanted to simplify cotangent pi over 2 minus theta times secant pi over 2 minus theta.
Tangent times cosecant?
Hmm?
Tangent theta times cosecant theta.
Tangent theta times cosecant theta. Not quite done yet, though. Remember strategy 1? Convert everything to sines and cosines. Sine theta over cosine theta times cosecant is 1 over sine theta. Right? So this is just 1 over the cosine or secant theta. We just put it over here. This is a lot of what we're going to be doing. And taking some expression, sines and cosines, and seeing if we can simplify it or convert it to some other form. I know you guys are a little worn out. I have a handout that has some problems.